Hello, all my dear students. I welcome you all to Check Academy Just a Minute series. In the series, every minute of your time help you in exam concepts. So our today's topic is Ampere Circuital law. As you can see that the statement of the Ampere Circuital law is written. It states that the line integral of the magnetic field around any closed path in the free space is equal to mu naught times the current enclosed by the loop. And that loop is basically called Amperian loop. So mathematically, how do we represent it? We represent it line integral of magnetic field over a closed loop is equal to mu naught time, which is called magnetic permeability of the free space, multiplied by the current enclosed by the Amperian loop. What is Amperian loop? What is Amperian loop? Amperian loop is basically imaginary loop which you draw across a current carrying conductor. If you remember Gauss law, in Gauss law, it was not a loop, it was surface, right? It was a surface, Gaussian surface. Here we use the term Amperian loop. Let's try to use this mathematical statement in the derivation of magnetic field due to an infinitely long current carrying conductor. Okay, students, let's derive the expression for the magnetic field due to an infinitely long current carrying conductor by using Amperian Circuital law. See, understand that what is the role of this law? This law basically uses symmetry to find out the magnetic field due to a current carrying conductor in a simpler way. Same thing was done by Gauss law. Find the electric field due to a charged body in a simpler way. Let's find out how. So here we have an infinitely long current carrying conductor. The current flowing through this conductor is I. As you can see that a dotted loop. So this loop is basically an imaginary loop which is called Amperian loop. So this is called a Amperian loop. Now, I need to find a magnetic field at the point P due to this infinitely long current carrying conductor. So, at point P, which is at a distance r, at point P, which is at a distance r from the current carrying conductor, I will take a small current carrying element. I will take a small current carrying element whose length will be dl. And at this point P, a magnetic field due to this infinitely long current carrying conductor will be in what direction? Will be tangential to this. So magnetic field at this point will be tangential and your dl vector is also tangential at point P. So we choose the Amperian loop in such a way that the magnetic field and the dl vector should be tangential so that the angle between them is zero. So if I write down the Ampere Circuital law, line integral of magnetic field is equal to mu naught times the current enclosed. As the magnetic field is uniform, you can move the magnetic field outside the integration. So it will be equal to integral of dl, which is mu naught. Now, what is the integration of dl? Dl means small part of this loop. When you integrate all the small part of this loop, what do you get? The circumference of this loop. So what is the circumference of this loop? 2 pi r. So V into 2 pi r will be equal to mu naught into current enclosed. So the magnetic field due to an infinitely long current carrying conductor is mu naught I by 2 pi r. As you can see, very simple, by using very simple equation, that is B dot dl equal to mu naught I, we very quickly, within 10-15 seconds, you can derive the magnetic field due to an infinitely long current carrying conductor. Now let's take a very interesting question on this topic, which will make sure that your concepts are perfectly clear. Let's move ahead. Students, as you can see the next question, we have a current carrying wire. The radius of the current carrying wire is A. You need to find out the magnetic field due to this current carrying wire at a point which is inside and a point which is outside. If you remember, it is similar to the electric field due to a charged hollow sphere at a point inside on the surface and outside. Let's understand this concept. So for a point which is outside, you can see that the point which is outside is P. So I have taken a Amperian loop whose radius is small r. So if I apply the first case, that is for a point where r is basically greater than a, that is outside point. So I will write down line integral of b dot dl equals to mu naught into current enclosed. If you see the figure carefully, the Amperian loop is containing the whole current carrying wire. It means whatever current passes through this, same current passes through this Amperian loop. Current enclosed will be same as this I. Perfectly fine. So the moment I move the magnetic field, which is uniform outside the integration of dl will be equal to mu naught I. So what is the integration of dl? Just now in the previous slide we discussed, it is basically the sum of all the small elements of the loop, which will hence give you the circumference of the loop. So this becomes b into 2 pi r equal to mu naught into I. So b equal to mu naught I divided by 2 pi r. So this is for an outside point. So for outside point, what can you say? That the magnetic field is inversely proportional to the distance from the center of the conductor. Now, what about for a point which is inside? So for an inside point, what we will do, for inside point, you have to be extra careful. For inside point, the current which is flowing through the inner Amperian loop will not be same as the current passing through the wire. As you can see in the figure, this is our inner loop. This is our inner loop. So the current which is passing through the inner loop will not be same as the total current. So let's find out the current flowing through the inner Amperian loop. What concept will we use here? What is the concept? The concept is current will be different, but current density will be same. So if I find the current density for the current carrying wire, it will be current divided by area. What is the area? Pi a square. And the current, let's assume that current flowing through the inner Amperian loop is I dash. Its area will be pi r square. So I dash will be equal to pi we can cancel. I dash will be equal to I into r square by a square. This is the current. Now you don't have to do this much. You can directly write this step. And here, instead of this current, you will put this current. So if I write directly, B into 2 pi r equal to mu naught into I dash. Only current is changing, that's it. And you found the current by using current density. So magnetic field will be equal to mu naught into I r square by a square divided by 2 pi r. When you simplify this, r square r gets cancelled. So magnetic field is mu naught I r divided by 2 pi a square. This is the magnetic field due to a current carrying conductor at a point inside it. Mu naught I r by 2 pi a square. If you observe, a is the radius of the current carrying wire, R and B in this case are directly proportional. So our final statement for inside is magnetic field at any point inside the current carrying wire is directly proportional to R. And understand that this time the wire is of finite length, not infinite. In the previous case, we discussed infinite, which is mu naught I by 2 pi R. Here it is a finite length. Now, for outside, inversely proportional. For inside, directly proportional. If they ask you to plot the graph, how will you plot the graph? Okay, students, let's draw the graph. As you can see that for the inside point, directly proportional. For the outside point, inversely proportional. So let's draw the graph. For inside point, directly proportional. And for outside point, inversely proportional. So this is B, directly proportional to R. This is B, inversely proportional to R. This point will be what? This distance. So first of all, mark the axis. This is R. This is B. So this is for inside, this is for outside, and what will be this point? This coordinate will be A. So if they ask you magnetic field will be highest at which point, it will be basically on the axis. After that, it will decrease. So make sure that do not mug up this graph. Important thing is that you learn how to derive the expression, because the same kind of graph you would have seen electric field. So you can basically mix up both of them. So be careful and learn the concept rather than just mugging up the final result. So one question I'm giving you as homework, what you guys have to do, you need to find the magnetic field at a point, a distance of a by 2 above the surface and a by 2 below the surface. I'm repeating the question again. Find the magnetic field at a point which is a by 2 above the surface and a by 2 below the surface. Write down your answer in the comment box, and next video we'll discuss some more concepts which will help you enhance your board exam concept. See you, students.